All right, this is going to be a review of Hardy-Weinberg equation and Hardy-Weinberg equilibrium. This dude right here is Hardy. He was an English mathematician. This dude right here is Weinberg. He was a German physician, and they both came up with the same basic concept or equation for how to model the genes within a population. So their model, their equilibrium, basically allows scientists to determine whether or not evolution is occurring in the population. And by that we just mean it allows them to measure the changes in gene frequencies over time. So if there's no evolution occurring, then the gene frequencies are going to remain constant. So it makes five big assumptions, that there are no mutations within the population, there's no gene flow, so no migration into or out of the population, that there's random mating within the population, there's no sexual selection at all, that the population is infinitely large, and that there's no selection on the trait that we're looking at. So you can see that this is a never going to happen type situation, or an almost never at the very most, almost never. And so we're basically making our null hypothesis here. Our null hypothesis is that there is no evolution, and we go ahead and we investigate the gene frequencies, and then if they're not the null hypothesis, there's the bell, then we go ahead and we look at what's happening. So if you look at this little population here, obviously there's not random mating. They're clearly sexual selection based on the type of organism. You know, they're kind of pairing up by color there. So let's do a couple quick examples just as a reminder. P plus Q equals 1. And remember, if I squared P plus Q equals 1 and I square the whole thing, then I would get this equation right here, where P is the dominant allele and Q is the recessive allele's frequency. This is important, the recessive allele frequency. Also, Q squared is the number of recessive individuals. That is Q squared is Q squared, Q. And these are both frequencies. So here's the deal. If they give you the frequency of an allele in a population, then they're giving you Q. If they give you the number of individuals or the percent of individuals in a population that are recessive, that's Q squared, and that's going to be important. So if 98 of 200 individuals in a population express the recessive phenotype, what percentage of the population are homozygous dominant? So the way that we would calculate that is 98 out of 200 is going to equal our Q squared value. So that's going to be 0.49, because 98 divided by 200, 0.49 equals Q squared. So Q is going to be the square root of 0.49, which is 0.7. If Q is 0.7, P plus Q equals 1. That means that this is 0.3 plus 0.7 equals 1. So P has to be 0.3. So it's asking us homozygous dominant. Homozygous dominant individuals are P squared. So that's going to equal 0.3 squared, which equals 0.09, which is a whopping 9%. And then what percentage are heterozygotes? That's 2PQ. So I'm going to take 2 times P times Q, which is 2 times 0.3 times 0.7, and that's going to equal 42% heterozygotes for 2PQ. So let's do two more practice problems. The first one, brown hair is dominant to blonde hair. If there are 168 brown out of a population of 200, that's the dominant frequency. And it wants to know what's the predicted frequency of heterozygotes, what's the predicted frequency of homozygous dominant, and what's the predicted frequency of homozygous recessive. So the first thing we need to do is the recessive. So if 168 are dominant, that means 200 minus 168 equals 32. 32 are going to be blonde, and that's what we want to start with. So 32 out of 200 is going to be Q squared. So that is going to give you 32 divided by 200 is what is that? I don't know. I have to type that into the calculator. 32 divided by 200. 0.16. Okay, and then my Q value there is going to be 0.4, because the square root of 16 is 4. And then remember, P plus Q equals 1. So if Q equals 0.4, then what is P? It has to be 0.6. So let's go back to our question. What's the predicted frequency for homozygous recessive? That's going to be Q squared. So that's 0.16. I can answer that. What's the predicted frequency of homozygous dominant? That's P squared. So that's going to be 0.6 squared, which equals 0.36. 0.36. And then what's the predicted frequency of heterozygote? So that's 2PQ. That's 2 times 0.6 times 0.4, which is going to equal 0.48. So that's 48%. 2PQ equals 0.48. And if you add all those up, 0.16 plus 0.48 plus 0.36, that should equal 1, which in fact it does. So that checks out. And one more problem. Now let's say blonde occurs 36% of the time in the population. Blonde is still recessive, so that's little b, so we're looking at Q squared equals 0.36. So Q here is going to equal 0.6, and that's going to be the frequency of the lowercase b, so 0.6, and then the frequency of the other one is going to be 1 minus 0.6, which equals 0.4. So really we just flip-flop the percentages from the previous problem. The predicted frequency of heterozygotes, 2PQ, equals 2 times 0.4 times 0.6, which equals 0.48. That's 0.48. And then what's the frequency of homozygous dominant? That's P squared. So 0.4 squared equals 0.16. So that equals 0.